So this is the ninth lecture for ECE 341, random processes. In the lecture today, we're going to talk about the multivariate Gaussian distribution. It's a pretty cool distribution. Gaussians are found everywhere in nature, and so it's one that gets a lot of utility for almost any discipline. A vector notation, some of the linear algebra topics that we talked about before, is very helpful here. I'm going to just put down a little bit of preliminary stuff, and then we'll lecture per normal, and I'll write it out real time. So we're going to go ahead and say that vector x, which is an n by 1 vector, is a multivariate Gaussian, and it has a mean vector mu and a covariance matrix Cx if and only if its joint probability density function takes a particular form. And the particular form here is that fx is equal to 1 by 2 pi raised to the n over 2, and then we're going to multiply that by the square root of the determinant of the covariance matrix. And then there's that exponential that we expect that involves x squared terms, but it's done matrix style. So minus 1/2 x minus the mean transpose times the inverse of the covariance matrix times x minus the mean of x again. And for this to work out, it does require that the determinant of Cx be greater than 0. Really all this is doing is it's making sure that no element in our vector x is only a linear combination of other x's, meaning that we have a full rank matrix Cx basically. Okay, so let's look at one particular case that we could have expected. We had seen in the bivariate Gaussian that having covariance equaling to 0 resulted in independence. We certainly should get the same result here for the n-dimensional. So we're going to go ahead and take a look at this idea of having 0 covariance, or covariance of 0 between any pairwise elements. So if we let then the covariance between xi and xj, for example, equal to 0 for all I not equaling to j, right? Then what do we know? We know that the covariance matrix itself has to just be a diagonal matrix, so we can write that out as a diag. And what's going to go on that diagonal is the individual variances of each one of those elements in x. So sigma 1 x all the way down to sigma n squared. Once we have that, we can easily get, once we know it's a diagonal matrix, the covariance matrix inverse, right, is also going to be a diagonal matrix, and it's just going to be the reciprocal of each of those elements. So we're going to get a 1 over sigma 1 squared going all the way down to a 1 over sigma n squared, which we could write, as a simple diagonal matrix. The last little bit that we might say in here is that we would look at, because we know that this is necessary, we need something about the determinant of that covariance matrix. Because it's a diagonal, only with the main diagonal, that determinant is really easy. It's just the product. And if this doesn't seem obvious, just do a quick review on your linear algebra. It's just a product of all the diagonal elements, which in this case are just the variances, sigma sub I squared, where I runs from 1 to n. Okay, what else did we get out of this? If I look at that term that was in the exponent of x minus mu x, right? Transpose that guy times the inverse of cx, right? Times the x minus mu x. If we take that whole portion of that argument of the multivariate Gaussian PDF, we end up getting this being equal to a summation I equaling 1 to n of the xi minus mu I divided by sigma I quantity squared, something along those lines. Okay, so what can we do with all of this? We can plug all that sort of stuff in, and we see that that joint distribution fx of x then can be represented as a 1 over, we're still going to have that 2 pi to the n by 2 out front. We're still going to have that determinant Cx to the 1/2, but the determinant was just a product. So we're going to have a product 1 to n, right, of my sigma I squareds square rooted. And actually what we get on that is just a product of the sigma I, or we can bring that 1/2 into the other. And then we multiply that by exponent of what? Well, that product term that we'd seen before, x minus mu x times the inverse of cx times x minus mu x, can just be done as a, well, we have the 1/2 out front, but we get a summation, right? And we're going to get a summation I equaling 1 to n of the xi minus mu I over sigma I, that quantity squared, and we can close this out. I would say that it probably is a little bit more helpful, if you want, if we move that 1/2 on the inside. So I'm going to go ahead and do that. I'll just move that guy on the inside, something like that. Doesn't really matter where we get it. Okay, well, we have here a way of breaking this up as well. An exponent of a sum can be written as a product of exponentials. And for each one of those n terms in that product of exponentials, we can steal one of those 2 pi to the 1/2 and the corresponding sigma I squared square rooted as well. So this whole thing can be written in as a single product going from 1 to n of what? I'm going to have 1 divided by, and it's going to be a square root, and I'm going to actually write it as a square root this time, of 2 pi sigma I squared times an exp of our minus 1/2, and we will have xi minus mu I divided by sigma I quantity squared. So just with a little algebra and knowing that covariance matrix was 0, knowing the covariance matrix, not the covariance matrix, knowing the covariance between the different elements of X were 0, that meant that the covariance matrix was diagonal. Given that diagonal covariance matrix, it gave us a very nice structure in the joint probability density function fx, which could be written out as a product of terms. It's a product 1 to n of very similar looking terms. And if you take a look at each one of these are each PDFs. These are PDFs of normal, right? Mu I, sigma I, Gaussians, right? Those Gaussian RVs, right? Which are also the marginal distributions. So we come with what we expect, or we could then say that this joint distribution, this joint multivariate Gaussian distribution can be written as a product 1 to n of my fxi of xi, because each one of those is the corresponding marginals, right? These ones up here that I'd written before, the PDF of a normal mu I sigma I Gaussian RVs, those were the marginal marginals. They were the marginals, right? F sub xi of xi, something along those lines. So we end up getting that in the case that we have the covariance, right? That was for when the covariance of xi comma xj equaling to 0 for all I not equaling to j. So as long as they were uncorrelated, the different elements of x, right? Then we know that the joint distribution is a product of the marginals. And whenever we have that, we know that we get independence. So we see, right, that if we have uncorrelated Gaussians, right, they are also independent. This is a not common kind of result. Most distributions would not have this. Being uncorrelated isn't enough to give you independent in most distribution cases, but with the Gaussian is. There's some other things that we can do with this multivariate Gaussian. So we're going to use a little bit of what we learned before. So I'm going to just say using what we learned before. If X is an n-dimensional Gaussian, right? So that multivariate Gaussian with a mean vector mu x and a covariance matrix Cx, and if we create a new vector y, right, that is equal to some matrix A times x plus that offset b, so a linear transformation on x basically, then we know what? We know y is distributed as a Gaussian. It is distributed as a Gaussian with what? Well, it's mean mu y. We saw what happens under linear transformations to the mean and covariance matrices. It's going to have a mean mu y being equal to A times mu x, right, plus that offset vector b, and that the covariance matrix for y is equal to A times the covariance matrix for x times A transpose, right? We know that from before. So we knew this part, right? So we knew this. This was from previous lecture, right? Previous lecture. The fact that it is Gaussian, that guy is proven in the book. You might remember that I made a proof of a univariate case where we had a univariate Gaussian under linear transformation also maintaining its Gaussian distribution. It was just algebraically tedious. It's even more so tedious for the multivariate case. And so we'll go ahead and let you read the proof in the book if you like, but it's the same result as we saw for the univariate case. Okay, so what do we get out of this? If you had a Gaussian multivariate and you do a linear transformation on it, you get a multivariate Gaussian coming out, right? So the distribution type is, I don't know where that just came from. The distribution type is still Gaussian, and then we also know what its mean and covariance matrix are through simple linear algebra kind of operations. What are other things that we know about the Gaussian? We know that the Gaussian as a distribution is a little tricky to compute probabilities from. In the univariate Gaussian case, you would have an integral of its PDF over some particular regions, and those generally do not have closed form solutions, and so we have to do some sort of numerical integration. The same is true for a multivariate Gaussian. If you're trying to find probabilities associated with that multivariate Gaussian, you end up having to do numerical kind of integrations, except for now they're n-dimensional numerical integrations. And that definitely can get to be sort of painful. So for the same reasons that we liked a standard normal for the univariate case, we also like a standard normal for the multivariate case. So we can talk a little bit in this particular case. So I'll just say that this is also useful. It is also useful to think about a standard normal vector. Standard normal vector. And we're going to define that standard normal vector as z. We'll still use a z on this. It's going to be distributed as a multivariate Gaussian, right? It's going to have a mean vector of 0, and it's going to have a covariance matrix just being equal to the identity matrix. Think about what it means to have that as an identity matrix. That means that for each element in the standard normal, it has 0 mean unit variance, right? The off diagonals of an identity matrix are all 0. That means the covariance between any pair of elements of that vector z are uncorrelated. And because they're uncorrelated, we know that they're independent. And because they all have the same mean and all have the same standard deviation or variance, we have a collection of independent and identically distributed Gaussians, all with 0 mean unit variance, something along those lines. That's what our standard normal vector is. So what can we do with this guy? We can relate this to an arbitrary Gaussian, and we'd like to be able to go between the two. Matlab is really good. We already saw this before. Matlab is good at making a standard normal. You just use the rand function in, right? But we might not only want to have standard normal, we might want to have an arbitrary kind of distribution. So being able to take that standard normal and compute a arbitrary multivariate normal is certainly worthwhile. And then maybe going the opposite direction is also useful. Being able to take an arbitrary distribution and return it to a standard normal would allow us to take advantage of just looking at probabilities using normal probability tables. So let's take a little bit of a look at some of these ideas. What we can do on this is that we can say for an arbitrary Gaussian random vector, x, and a matrix A such that A times A transpose is equal to a desired or given covariance matrix, then we can say that a standard normal can be gotten from A inverse times mu minus its mean, something along those lines. Or we could write this as solving for x, we could write I could say this, or x is equal to a z plus mu x. You might recognize this. This is like a derived random variable is a linear combination of the standard normal. The matrix A still looks like the matrix A. The vector B is just that mean vector. And if you go back through what is the resulting mean vector, you'd see the resulting mean vector of x was mu x. I'm working with this expression down here. So we had something that was zero mean and unit variance and no correlation. We do this transformation, we would get a random vector x that has mean mu x, and its correlation function would be A times the original correlation, which was just the identity matrix, times A transpose, which we said was equal to the desired one, Cx. So what comes out of this guy is distributed normal, right? Mu x, comma, Cx, something along those lines. So it's a way of relating standard normals to an arbitrary normal, and it's very similar to what we saw in the univariate case. If you had a univariate standard normal and you multiplied it by the standard deviation, kind of like the square root of the variance, the square root of the covariance, you could think of, right? That's an a times a prime is sort of like an a squared. That gives us the desired covariance structure, and then we add onto that the mean vector to give us the desired mean on there as well. So a simple relationship or pair of relationships that relate a standard normal vector with an arbitrary Gaussian, or we can get an arbitrary Gaussian from that standard normal vector. What does it require? It requires that we know what we know our mean vector is. Usually that's not a problem, but then we also need to have this A, right, such that A transpose is equal to the desired covariance. And usually we have that desired covariance. That's no problem. So we usually know the mean, we usually know the covariance, but we need to be able to get an A, a matrix A, such that that matrix A times its transpose, right, ends up giving me that overall desired covariance matrix C sub x. Well, we can determine, or we can find, we can obtain the value A, maybe I shouldn't call it a value, maybe I should call it the matrix A, using a little bit of a sophisticated linear algebra concept or technique called a singular value decomposition. So we can obtain the matrix A using a singular value decomposition. It seems that in recent years, most of the linear algebra classes are not talking about singular value decompositions. It's usually a more advanced topic for a later, more advanced linear algebra class. Most linear algebra classes do talk about the eigenvalue and eigenvector problem. They do talk about things like semi-definiteness and the like. And so I think people would have the background to do some of this, but we're just far enough in the semester. I don't think I'm going to go through a full out on this. You can read about these singular value decompositions, sometimes called SVDs, in the back appendices. In the book. So if you took a look back there, they have a big discussion about these SVDs and some of the properties associated with it, and I'd give you a little encouragement to do that. How are we going to do it? Matlab. So Matlab has a built-in SVD function. So there's a built-in function in Matlab that will do a singular value decomposition, and it will break up for us the matrix in the way that we need so that we can get a value A. And we'll show an example here in just a minute. It kind of looks something like this. So we could say something like this. Thus, I skipped a bunch of proof in here, so the thus is following a bunch of proof in there. We could sit there and say that any old covariance matrix, it has a particular structure. This covariance matrix can be represented as a UD, these are each matrices, and that D is going to be to the 1/2 times a UD to the 1/2 transpose. And really this UD here is going to be my A, and this is going to be my A transpose. And where do those UDs come from? Those UDs come from our singular value decomposition. So in MATLAB, we would have something like this. We would have this idea of a U, and if you read the Matlab documentation, they use a little bit different notation. They will say in their help file U, S, and V, something like that, equals SVD, and you would pass into that guy your covariance matrix, something like that. So you pass in the covariance matrix in there. This S really from Matlab is going to be like our D that we would want in there, something like that. The U is our U, and V for us, we're going to find out due to the structure, on CX. And there's really no need for you to know this or really care too much about the details, but covariance matrix CX has some structure. We know that it has some symmetries, right? The covariance terms off diagonal to the top and to the right match in kind of this symmetric way the covariance in the lower triangle, the ones to the left and below of the main diagonal. And those symmetries correspond to some structure as well in the singular value decomposition. So due to that structure in the covariance matrix, what we do find is that U is equal to V. So we could use either the U or V that Matlab pops out, but if you do a help on SVD in Matlab, it does require three arguments coming out, U, S, and V. You can do an SVD on other kind of matrices other than just covariance matrices, ones that maybe don't have that same structure, and you'll get something a little bit different. But for a covariance matrix, which has those structures built in, the main diagonal has to be what? All non-negative elements that correspond to variances, and then there's that symmetry off diagonal. In those particular cases, U and V will come out the same, and we do find out that we can get then this covariance matrix being equal to U, right, times the square root of S times U square root of S transpose, right? So if we did all of that, you could have U, and go ahead and put in your S to the 1/2, right? And then you're going to do a U S to the 1/2. Basically, our Matlab S is the same thing as the D that I talked up there, diagonal. It will come out as a diagonal matrix transpose. What happens when you transpose things? You end up getting stuff like this. You would get an interchange of the order. So you can go back and check your linear algebra on this. You'd get an S to the 1/2 transposed, right? And then you would get a U transpose, something along those lines. And a transpose on a diagonal matrix is still a diagonal matrix. So I'm going to get S to the 1/2 times S to the 1/2. That's just S. So that's like a U transpose that comes out of this guy. And out of that whole thing, that thing becomes CX. This is all buried in that kind of some of the theory and background on SVDs that we're not fully going to cover, but I'm going to try to re-summarize here in just a minute. Any covariance matrix, So summary. Any covariance matrix CX can be decomposed as CX equals A transpose, where we can get A is being equal to U S to the 1/2. That's supposed to be a 1/2. A US to the 1/2, the square root of that diagonal matrix, right? Which, using a slightly different notation, something from the book, is a UD to the 1/2. The book just calls it D for a diagonal matrix, UD to the 1/2. That comes from a singular value decomposition. And we can think of that in Matlab as USV is being equal to the SVD, right, of our CX. And then we would just take U times the square root of S, something along those lines. Once we have that then, right, what can we do? We can use that to transform a standard normal vector into an arbitrary one, right? And be able to use all the benefits of having that standard normal as well. So A, was equal to, and I think we did say this, yeah, we did, so we don't have to repeat it. A is equal to u times the square root of d. For then, right, an x with some covariance matrix Cx, right, we can convert to z by what? Z equals the inverse of that matrix A times x minus its mean vector, right? So that's the way we can get the standard normal out of an arbitrary one. Alternatively, we can obtain, right, a distribution, a desired multivariate Gaussian, from Z according to, right, here we're going to have x is being equal to a z plus our b here is just mu of x, something along those lines. So we can go either direction. If you're starting out like in Matlab and you just have standard normals that can be easily generated, but you need something arbitrary, you can easily get those by finding the value or vector, the matrix A, using your SVDs and knowing what your mean vector is that you want. Or you could take something that was kind of an arbitrary multivariate Gaussian and you can convert it to a standard normal, and that facilitates finding things like probabilities. So let's do a very quick example of this, and then we'll call it a basically done deal for this lecture. So let's go ahead and do this. We want to generate observations of a two-dimensional normal distribution. So a multivariate Gaussian with two elements with the following. I would like to have a mean vector be equal to 1 and minus 1. So these are not zero mean cases, right? We are going to have one with a mean of 1 and the other one's going to have a mean of minus 1. And we're going to go ahead and have a covariance matrix being equal to, let's let it be 1, 1/2, 1/2, and 1. What does this tell me? If I remember right, this first element, right, that's what? That's sigma 1 squared, the variance of my first element in that vector x. So if I looked at x, right, as being some x1 and some x2, I know both x1 and x2 are Gaussian. x1 is a Gaussian who has a mean, right, that's mu x1. It's going to have a mean 1 and a variance equal to 1. x2 is going to have a mean, right, so that's my mu x2. It's going to have a mean minus 1, and it has a variance, that's my sigma 2 squared. So that's the variance of my second element. It's also going to be 1, both unit variance. And then what do I have over here? I have a covariance. So here I have my covariance term. That covariance term, because it's not 0, means they are not independent. I have a covariance that's greater than 0. That gives me a correlation coefficient that's greater than 0. There should be straight line dependence between these two. So as x1 gets larger, so too should x2 get larger. Okay, so how are we going to end up doing this? I would like to generate, so we will use the transform. We can get these observations x as being equal to a z plus b, right? The linear transformation on these. Clearly, we know what the b is, right? Clearly, b is just going to be equal to our mean vector mu x, which is 1 and minus 1. Next, we're going to try to find the matrix A so that we can do the transformation. We know that A comes through a singular value decomposition of the covariance matrix, which we didn't know. We said we wanted a covariance matrix that was going to be 1 on the main diagonals and half on the off diagonals. So I'll go ahead and just use what the Matlab code would be. Next, then we'd go ahead and use Matlab. We would go ahead and say Matlab, pass back those parameters U, S, and V that come out of a general singular value decomposition. What do we pass to that singular value decomposition? We pass it the correlation matrix. or the covariance matrix. That's going to be 1, 0.5, skip down to the next line, 0.5, and 1. So we do the SVD of that covariance matrix, and MATLAB's going to kick out some values. So from MATLAB, right, from MATLAB in this case, you can easily do this in the MATLAB environment yourself. So from MATLAB, we would get the following things. We would get U, and we had already mentioned that for this particular case, because of the structure, the regularity of the covariance matrix that you pass to that SVD function, U will be the same as V. And in this particular case, MATLAB will kick out a value -1 over root 2, and it will have a minus 1 over root 2 again. And then if you go down to the next line, it's a minus 1 over root 2. So pretty boring so far. But the last one spices it up a little bit by getting rid of that minus sign. It's just a 1 over root 2. The S value that MATLAB gives back, the S value on these things, so the S value that MATLAB gives is going to be a value 1.5, 0, 0, 0.5. We said the S there, which from kind of the book notation, this is our D, if you will. That's our D, is that MATLAB S, if you did the help on the MATLAB stuff. It is a diagonal matrix, right? And so what do I know? I know that that matrix A that I desire, so I can complete out that linear transformation, that matrix A is just the matrix U times the square root of that diagonal matrix S. And so what would I get in this particular case? If I did the U, that U is 1 over root 2 with a minus, 1 over root 2 with a minus, 1 over root 2 with a minus, and 1 over root 2. That's the U. And then the S, we know, is 3/2 and a half on the diagonal, but we're taking the square root. So that's going to be root 3 over 2, 0, 0, root 1 over 2. Something like that. And I just need to multiply these guys through. So if I do the first one, I take that first row of the A matrix times the first column of that square root of S, and I'm going to get minus 1 over root 2 times root 3 over 2, right? And so I'm going to get something like root 3 over root 4, and I can write that whole thing as, well, just minus root 3 over square root of 4 is just 2, so I'm going to get root 3 over 2. Same sort of way, if I go and figure out the next one, it's going to be a value minus 1/2, because I just get minus 1 over root 2 times 1 over root 2. So the root 2's will multiply each together to just give me a 2. The next one down, I use the second row of A times the first column of S, and I'm going to get a minus root 3 over 2, and the last one I'm going to get is a 1/2. So there's my value of A. A little bit goofy, right? So A equals minus root 3 over 2, minus 1/2, minus root 3 over 2, and 1/2 in the final one. So what do I know? I know that if I take X as being equal to A times a standard normal, which MATLAB could easily give out, plus that vector B, which was just the mean vector. Nothing hard about getting that. Everything that was difficult here was finding that vector or that matrix A. If I do that, that should be distributed as a normal, right? Multivariate normal, whose mean, right, is going to be that mu x that we had specified and that covariance C of x. How could I test this? I could test this in MATLAB pretty easy. I could go ahead and just let x be equal to A. Go ahead and compute that as we had before, A times a rand n, for example, 2 comma 1. What does this give me? 2 rows by 1 column of the standard normal. So that's going to be my z. It's a 2-element z vector, right? And then I would add into it the b, which we had already set up as being 1 and minus 1, something like that. If I repeated this a whole bunch of times, I could look at how these guys were distributed, and I could verify that they indeed are normally distributed and that they have a correlation. I've done this in MATLAB, and I've got some MATLAB code that I'll share with you when I send out the links for this. And that MATLAB code is going to do not only this one with a correlation being equal to 1/2. So if we go back up here to what our original was going to be, we said that we were looking for, in this particular case, a correlation value of 1/2. My code is also going to go through the cases of a correlation value equaling 0.8 and another one being equal to 0.95. So I'll look at 3 different cases. I'm going to generate 1,000 observations for each one of these 3 cases. I'm going to look at those pairs of points because I'm going to take standard normals two elements, standard normals, convert them using this linear transformation, and then take a look at the pairs of resulting values that come out, x1 and x2. I'm going to do that 1,000 times over and get some scatter plots, and we'll be able to see definitely those correlation values coming in. We'll also estimate the marginal distributions, essentially, just by doing histograms on the individual variables x1 and x2 across those 1,000 observations. So let's go ahead and do that. Let's take a look at, so we'll look at some Matlab simulation to finish this out here. So Matlab simulation. So let's take a look at that Matlab simulation. Coming over to Matlab, I've already run this stuff, so here's the code, and this is going to be emailed to you as I had mentioned before. We'll just run through it really quick. I go ahead and set the seed for my random number generator, then we'll be able to ensure that we can repeat the results and that I'm not cheating you. I'm going to go ahead and make it so that I create 1,000 observations, and because these are vectors, right, they're going to be two length vectors, I'm going to actually create 2,000 points each time I do this. We knew what the mean vector was. We said that that mean vector, which was that part of the linear transformation, that vector b, was just going to be 1 for the first element minus 1 for the second. So my first random variable x1 should have a mean 1, and my second random variable x2 should have a mean minus 1. I'm going to create the covariance matrix here. I'm going to let it be a function of a arbitrary covariance term. So if I look at the covariance between x1 and x2, I'm going to let that be rho, and I have then my covariance matrix being 1, rho, and then rho, and 1, something along those lines. And then what am I going to do? I'm going to pre-allocate some space for this resulting vector across all the observations. Number of points there, 1,000, and they're each a two-size vector. And then I'm going to just have an index to keep track of my different cases. So what are the correlation coefficients that I'm going to be looking at? I'm going to be looking at 0.5. That was the one that we did kind of mechanically to find the cap A that would result in that, and I'm going to do 0.8 and 0.95. Here's where I do that SVD, right? Just according to what we showed in just a few minutes ago. But now I'm going to allow it for each of those three different cases. I'm going to let my A be U times the square root of S. We had also shown that. And then for every single one of those 1,000 points that I do, I'm going to create a set of observations of my random vector X, which is in this case 2 in size, and I'm going to do it 1,000 times over. A times the standard normal, so that's A times rand n, right? And then I have that offset vector B. And then the rest of this, most of the rest of this stuff in here is just a bunch of plotting stuff so that we can see what it looks like. We're going to plot out, in this particular case, a histogram of the first random variable, and I'm going to plot out a histogram of the second random variable. These are estimates or kind of approximations to the marginal distributions of x1 and x2. They should be bell-shaped, right? x1 is just a single random variable. It should be Gaussian. It should have mean 1, right? And it should have variance 1. My x2 should also be Gaussian in shape, so it should have a bell-shaped curve in that. Its mean is minus 1, and it should also have a variance equaling to 1. And then I'm going to do a scatter plot. I'm going to plot my observations of x1 and x2, and what we should expect on there is that there should be some straight line dependence, and that straight line dependence should get stronger as the value of my correlation coefficient rho, right, gets closer to a value of 1. And so we can take a look at these and look at what the Matlab puts out. So I'm going to ask you right now, let's just go ahead and make it sort of big. We'll just start with this guy here. So this first one is the histograms, right, for random variable x1 and random variable x2 for the case of the correlation coefficient equaling to 0.5. So here is my x1 stuff, and here is my x2 stuff. And so these are estimates of, you can think of these as sort of like an estimate of the probability density function for x1, right? Based on the observations. There's 1,000 observations, so just a simple histogram. What do I see? I definitely see that this thing follows a kind of Gaussian, like curve in there. If I look at where that peak is, that peak comes right down to that value 1 that I would have expected. We knew under transformation, remember what Matlab supplied to this. Matlab used the rand n function, which is generating 0 mean unit variance stuff. And what we come out of here is we definitely have something that's got, in x1 anyway, a mean that apparently looks pretty close to 1. In the same sort of way, these histograms are only based on 1,000 values, so it's a little bit hard here to necessarily perfectly see it They aren't going to be perfect, but if I come in here and there, and yeah, that seems about -1 as well. So it does seem like the means are about where they should be. Furthermore, if I wanted to know something about the variation here, are they spread out as much as they should? We knew that we were looking for something like sigma 1 squared being equal to sigma 2 squared. We're supposed to be equal to 1. So the variance was supposed to be equal to 1. That means the standard deviations are equal to 1. And we know that the bulk of a Gaussian distribution should be plus or minus 2 standard deviations. So at least from the mean. So take x1, its mean is at 1, right? That's here. And if I go over 2 standard deviations, there's 2, 3. So 1 and 1, that's 3. That comes out to about here. And then go out 2 standard deviations below the mean. So 0 and -1. That's somewhere around there. Does that contain the bulk of the observations? Absolutely. So that seems about dead on for what we'd expect for a random variable that has unit mean and unit variance. So a standard deviation equaling to 1, the bulk, 95% of the observations to be in that interval -1 to 3, right? 2 standard deviations away from the mean. In the same sort of way over here for the other one, it's sitting there at -1, come out 2 standard deviations and 2 standard deviations above, and yes, again, it seems to have the bulk. And in fact, if we look at this first case was for the correlation coefficient, we can't tell that yet, right? The marginal distributions don't have rho in them at all. So we know nothing about the correlation between these two. The marginal distributions by themselves is not enough to understand how they are interrelated. It just tells us how x is behaving by itself, x1, and how x2 is behaving by itself. If I go ahead and I take a look at other cases that come in here, this next one is for a correlation coefficient being equal to 0.85, and then the last one in here is for correlation coefficient being 0.95. 0.95 for this one, I think I just said 0.85, but it's 0.8 for this one, and then 0.5 for this one sitting here. All of these other ones have marginal distributions, these histograms, which are essentially the same. We can sit there and think of them being bell-shaped, right? There's that bell shape. Where's the peak there? That peak is at 1. Where's the peak at this guy? This guy comes in here something like this. We got that peak coming in here, and that peak coming in there is right around -1, and we get the same sort of thing over here. This guy's got its normal distribution, and its peak comes in there. That peak comes in at about 1, and this next one come down here is going to have something going out like that, and its peak comes out there at -1. So all of these guys look essentially like the same. If I gave you any set of these marginals, right, you would come to about the same conclusion, that they all seem to be normal. The left set of marginal distributions seem to be unit variance and mean 1, and the right side seem to be unit variance and mean -1. And beyond that, you can't say much. Well, the scatter plots tell a whole different story. So let's take a look at the scatter plot for the first one. This one is just the different observations of x1 and x2. So I have x1 on this axis, and I've got x2 over on this axis. And what do we see? We see that they're a loosely clustered set of points, and there absolutely, right, is a line kind of behavior in here. It's not going to be super strong because the covariance is a medium-ish value. It's 0.5 rather than getting close to those extreme values of 1. So we expect there to be some variation from that line, but there definitely is a line piece in there. You would not know, right, from either of these. It's just as possible that these guys could have been uncorrelated, right? In which case we would have had something over here that would have been more circular rather than more oval shaped. Now, what else do we see in here? Where is the kind of center point in x1? If I come in here and I find where I look and see about the center point of that bulk, come down to where that is. Well, that's the mean of x1 is 1, right? And come across that to the other one, and oh, that's that mean of x2 of being -1. So the bulk of these observations does seem to be centered at the mean of x1 and x2, as we would have expected. If we had not just had a bunch of scattered points, but we had built out the actual density function, right? We know that the peak of that density function would have been at the intersection of those two means. Now, when we go to the next set of observations, and if you remember the code, the only thing that differed there is I set the covariance equal to 0.8. I passed that to the SBD function, got a different set of values, U and S. From that U and S, I got a different value A, and that A is what transformed my standard normals into my observations X. What happens when I do that? Well, in this case, covariance equals 0.8. It is closer to that extreme value of 1, and we still see that straight line kind of dependence. And if we figure out where is kind of the center of mass in this guy, it's somewhere in there. And where does that occur? Mean 1 and mean, well, -1, so it's all the same stuff. But it's a skinnier ellipse now, right? Because the amount of linear relation is enhanced. And if I go to the last one, 0.95, we're getting really strong now at this point. It absolutely is still following along that same straight line. Line there is going to have a slope 1 because they both have unit variance. And if I look at the kind of center point of where that mass is, it does occur again at that intersection of the means 1 and -1. But now it's a really squashed out ellipse, right? If you know that you have a value of x that was equal to 4, right? You don't have much variation that you see in what's coming on your value of y in this particular case, right? Now, what is x of 4? That is 1, 2, 3 units off the mean. And where do I end up over here? I was at a mean of -1, and we could go up 1, 2, 3 units off of that up to about 2. This isn't the same scale. This one, the spacing on the horizontal is a little different than the vertical, but it's still along that 45-degree line if you actually drew it, where 1 unit in the horizontal was the same distance as 1 unit on the vertical. We can see that. Okay, so hopefully all of this has made some sense. Just a very, very fast recap then of what this lecture was about. We looked at something called the multivariate Gaussian. We gave without proof the joint probability density function, which could be represented using some vector and matrix type of parameters that have some pretty easy to understand interpretation. So we have things like mean vectors and covariance matrices, this sort of stuff. We saw that if all the off-diagonal elements of the covariance matrix were 0, then we had uncorrelated random variables, which in the case of a Gaussian means they're independent. And so we got a simplification. We found that joint distribution could be written as a product of the marginals. And then we played some games about how we could take a linear transformation, which we'd studied before, a linear transformation of a Gaussian to get a new Gaussian. And in this way, we can do things like convert an arbitrary Gaussian into the standard normal vector, or we could take a standard normal vector and convert it into a desired Gaussian, like we did in this particular example. In order for us to do that, we had to use this mathematical technique called the singular value decomposition. We skipped the kind of background math on it. It is connected to the eigenvalue problem. It uses at least some of the characteristics of our covariance matrix, which we haven't spent a huge amount of time on, but we know that, for example, the main diagonal has the variances of each of the elements of our random vector x, and then the off diagonal is all the correlation, the covariance terms, the correlation between the different elements of x. And so we were able to take the singular value decomposition and be able to get the transformation from that, the transformation matrix A, by which we could turn things like a standard normal into that kind of correlated set of observations, like the one that's showing right here. We had started with a two-dimensional unit variance, 0 mean, uncorrelated Gaussians, and we were able to create highly correlated, right? Highly correlated using this covariance 0.95 Gaussians with shifted means at 1 and -1, and maintaining the variance in this particular case. Next time, we're done with chapter 9 or 8. We're done with chapter 8 now. So next time we're going to switch over to chapter 13. This is on stochastic processes.